I'm going to introduce the trigonometric substitution method. And these are substitutions necessary to integrate certain integrals that contain something like square root of a squared plus x squared, or square root of a squared minus x squared, and square root of x squared minus a squared. The substitution is rather strange. For this type, you want to set x as a times tangent of u. And for this type, you want to set x as a times sine of u. And for this type, you want to set x as a times secant of u. Now, for each of these cases, you need to know what these will turn into. And in order to be able to do that, you need to know some trig identities. The most important one that's going to appear again and again will be the following. Cosine squared of u plus sine squared of u is equal to 1. And then if you divide this by cosine squared both sides, then cosine over cosine will be 1. What sine over cosine? Tangent squared of u. And then 1 over cosine is secant squared of u. Okay. So those are the two formulas that you'll be using over and over again. Cosine squared plus sine squared is 1, which of course everyone knows here, but the less often used one is 1 plus tangent squared is equal to secant squared. That will be also used. Okay. Now, these substitution looks strange for two reasons. One is like, usually your u substitution is u equals the function of x, right? But here you're setting x as a function of u. So that's one way it's weird. Another reason it's weird is usually when you do u substitution, you set u as something inside the integral that looks similar, right? But for these types, these substitution comes out of nowhere, right? And to understand why these substitutions actually work, you need to figure out what these are individually. So let's start with square root of a squared plus x squared, which is, in our case, x is a tangent of u, right? So you square this. Tangent of u squared, which is square root of a squared plus a squared tangent squared of u. And then you factor a squared out. You can factor a squared because they both have a squared. And a squared can come outside the square root as a. Oh, by the way, I forgot to talk about the assumption that a has to be positive. So when a squared comes outside the square root, it will come out as a. And then a squared is a squared times 1, so moving the a squared outside, you're going to be left with 1. A squared, when that gets moved outside the square root, you end up with tangent squared of u. Okay. Now what is 1 plus tangent squared of u? Right? That's what I said, that you use this. Now here's a slight technicality here. Square roots and squares kind of cancel, but it causes some trouble if the thing inside is a negative. So you may end up getting a times secant of u, but if this is negative, you need to put an absolute value there. Did you know that if x is less than 0, then absolute value of x is equal to negative x? You know that? That's pretty weird, right?
Actually, no, that doesn't make sense.
Yeah, because this is deceptive. Is this a positive number or a negative number?
It's a positive.
It's a positive number because we're assuming that x is negative, right? If x is negative, it looks like a negative number, but this is actually a positive number. So this is true. So in this context, if secant u happens to be negative, then this absolute value can be swapped by putting a minus in front, if this happens to be negative. But that unfortunate case won't happen for us, luckily. And the reason that it doesn't happen is the following reason. If you set x as a times tangent of u, the graph of tangent is like that, with negative pi over 2 and pi over 2. And the graph of tangent actually is a periodic function, so it repeats, which a priori doesn't have a inverse function. But if you restrict the domain to just from here to there, it does have the inverse, and that's how you define the inverse function. And because this is really saying that u is equal to tangent inverse of x over a, when you make this substitution, you're really restricting the domain of u in order for this to make sense. And luckily for us, when your angle is between here to there, this is from negative 90 degrees to positive 90 degrees, which is either the first quadrant or fourth quadrant. So if you go around the circle, you know, all students take calculus. We know that cosine is positive here and there. So for at least for this angle of u, secant of u will always be positive, and you're going to end up with a secant of u. All right, that was a bit too much, I think. If all that explanation was too much, just say, oh, there is some danger with canceling the square and square root, but for us, we don't have to worry about it, okay? So what I want to say is that in this case, square root of a squared plus x squared will become, what is it, a secant of u. And then let me try to do the other ones. What do you get if you solve this for u? So this gives you x divided by a, and then you apply the sine inverse. So it's sine inverse of x over a. And let's compute, for this one, let's compute square root of a squared minus x squared, where x is equal to a sine u. And this is important for you to try, so please take time to calculate this. Okay, let's try it. You plug in x equals to a sine u into x, which means you replace x by a blank, and in that blank, you're putting this in. That's what it means, right? And then you can simplify this as square will square the a, square will square the sine, so that when you factor the a squared out, it will be 1 minus sine squared of u. You still have a square root. And this a squared can come outside the square root as a. But what is 1 minus sine squared of u?
Cosine squared.
Cosine squared, because you have this identity. I told you that this is important, right? Cosine squared of u is 1 minus sine squared if you move the sine squared to the other side. Okay? So you're going to end up getting a times square root of cosine squared of u. But again, for this sine inverse to be defined, your angle must be between negative pi over 2 to positive pi over 2, again in the first and the fourth quadrant, where cosine is always positive. So this will end up being just a cosine of u. In other words, you don't need this absolute value. This will be fine. Okay, do you want to try this? Try. Oh, first, you solve for u by dividing by a and then applying secant inverse. So u is equal to secant inverse of x over a. Oh, and we just got that this is a cosine of u. All right, so please try this one. Square root of x squared minus a squared, with x being a secant of u squared minus a squared. Then a squared can be pulled outside as a, and you have secant squared of u minus 1. But then if you subtract 1 both sides here, we know that secant squared minus 1 is tangent squared, right? So this will become a times square root of tangent squared of u, which actually becomes, when you cancel the square and the square root, we talked about the fact that you need this absolute value, right? Now, here, the absolute value does make a difference. So what happens is that for the secant inverse to hold, your angle should be between 0 to 180 degrees, excluding 90 degrees because secant of 90 degrees is not defined. And that's like the second and the first and the second quadrant. In the first and the second quadrant, tangent is positive here, but tangent is negative here. So if you're in the wrong quadrant, that will turn out to be a negative a tangent theta, or a negative a tangent u. But that becomes so confusing that for our class, we will only deal with the case when x is bigger than a. Okay. If you assume that x is bigger than a, then you can make the argument that at the end of the day, you're in the first quadrant, and this will be just a tangent of u. And I don't even want to mention what happens if it's the other case. For this to be, for x squared minus a squared to be positive, it's either x bigger than a or x less than negative a. The other case will give you some minuses, and it's really confusing. So we're not going to do that case, okay? Anyways, this will become a times, what was it, tangent of u. Okay, so these are the things that are needed for trig substitution. And we spent a lot of time trying to figure out what these are. But for all these, the only thing that you want to memorize is this, the first two columns, okay? The other ones, you should just derive from these other formulas, okay? All right. Now, before I do an example, I also want to write some formulas that come up a lot that you should know. Okay, so first the one that we had, like a 1 minus sine squared theta, or 1 minus sine squared of u is cosine squared of u. B, 1 plus tangent squared of u is secant squared of u. C, tangent x prime is secant squared, yes. And secant x prime is secant x tangent x. You also need to know integral of secant x sometimes. And we did this a long time ago, but you probably forgot. Does anyone remember?
Secant x tan x?
No, that's the derivative.
Oh.
ln of secant x plus tangent x. Okay. Yeah, it's really hard. It's not so easy to get this. Okay, and then you need to know sine squared of theta is 1 minus cosine 2 theta over 2. And then G, cosine squared of theta is 1 plus cosine 2 theta. Okay, just one more. H, sine 2 theta is 2 sine theta cosine theta. And then there's one more, but it's okay. I'll tell you more trig formulas that's needed as it comes up. Okay. All right, so let's just do one example. Okay, example 1. Find the integral of 3 over square root of x squared plus 25. Okay, which one of these three is this one?
The first one.
The first one, okay. Except that here you have x squared in the second one, second place. So you should switch places and write 25 as 5 squared and write x squared as x squared. Then this looks exactly like this form, which means you want to set x as what times what? 5 tangent of u. Okay? All right. So this is the substitution that you need to do. And you would need to do the following. First, you have to find out what dx is. So you need to differentiate tangent of u. What's the derivative of tangent? Secant squared. And then you also need to know what this transforms it to. And I wrote it here so you can just use this, but really you want to take time to plug this into here to get the same thing. And if you do that over and over again, it will become much faster. Okay, so you don't want to memorize this table. Just memorizing this table will get you into trouble when it's an exam time and you forget this. Sometimes that happens, right? And then you don't have any ways to retrieve it. Okay? It's better to just remember this much and then get this. All right, but we'll just use it. So we know that this will become 5 times secant of u. And therefore, this integral will be 3 over 5 secant of u times dx is now replaced by 5 secant squared of u du, and then secant u cancels with the secant squared there, 5 cancels, so you just have the integral of 3 times secant of u du, and as I wrote here, it's 3 times ln of absolute value of secant of u plus tangent of u plus c. But wait, you need to go back to x, right? Since this is a substitution after all, in any substitution question, at the end of the day, when you write your answer into u, you have to go back to x. That's an additional step you have to do. And you do it by first looking at this right here. So what is secant of u? If you solve this for secant of u, you just divide by 5, right? So it will be 3 times ln of square root of 25 over 25 plus x squared over 5. What about tangent of u? X over 5, just taking this equation and dividing by 5, right? So it's going to be x over 5 plus c. And this is a full credit answer. Okay? If you write that, that's full credit. However, I want to show you that you can simplify this even further. And the way you can do it is by first rewriting this. So from here it's optional, okay? You can rewrite this as ln of square root of 25 plus x squared plus x divided by 5. But wait, that's a division inside the log, right? Division inside the log can be changed into
subtraction?
Subtraction of 2 logs, right? And by the way, you can also see that this will never be less than 0. So this, because this is bigger than just this by itself, but that's bigger. That's the absolute value of x. So even if x is negative, this plus this is never negative. So what I'm trying to say is that this absolute value is not necessary. So you can further rewrite this as 3 times ln of square root of 25 plus x squared plus x minus ln of 5 plus c, so that this becomes 3 times ln of square root of 25 plus x squared plus x. And then you have 3 times ln of 5, but that's some number, right? It's some number plus some arbitrary constant. So you can rename that arbitrary constant plus 3 times negative ln 5 as another arbitrary constant, c prime. Okay? But who cares if it's called c prime or c? We can just rewrite this as c. Okay? So although this function itself is different from this function, you can just absorb that extra constant into the other arbitrary constant, and this will be the fully simplified answer. Okay? But if you do this, this will be full credit.